Welcome to part 1B of our Hess's Law video podcast series. This is the second of 4 parts. We're talking about calculating enthalpies of reaction using enthalpies of formation tables. So what I'd like you to do is to engage a challenge problem that you'll see with the next slide, and pause the podcast where appropriate, try and work through this, and we'll see where we end up together. Okay, here is the problem. We have silicon tetrachloride liquid reacting with water, liquid water, to form silicon dioxide, which is a solid, and hydrochloric acid, which is a gas. Given the enthalpy of formations for each of the compounds above, calculate the delta H of reaction, which is the change in enthalpy for the reaction above. Now, I'd like you to pause the podcast, do what we demonstrated in part 1A of the Hess's Law podcast, and after you have solved the problem, come back, resume the podcast, and we'll go step by step and see if your solution matches mine. Thanks. Welcome back. Let's check your work and see how you did. The first thing when you're given the enthalpy of formations table as relates to the reaction that we're trying to solve is we want to write the equations that represent the formation of each of the compounds in the reaction from their constituent elements, and that is what's done here. When we do that, we treat the elements in their standard state, which means at 1 atmosphere of pressure and 25 degrees Celsius, and we just complete the table in this way. We add the reaction rather than just the compound name, showing the formation of the compound. And remember, it's 1 mole of the compound, which enables us to use fractional coefficients. So as you look down at the bottom equation, 1/2 H2 plus 1/2 Cl2 yields HCl. And one thing too, and I left this off, and my apologies for that, but if you would, in your notes, put the symbol for a gas next to the 1/2 Cl2 in that bottom equation, that would be much appreciated. Continuing along with the solution, my next step here was to find the coefficients from the reaction equation and make sure that the enthalpy of formation equations in my table have matching coefficients to those. So my SiCl4, silicon tetrachloride, is fine. My water is fine. My silicon dioxide is fine, but I'm going to need to get the number of moles of HCl to 4. And in order to do that, I'm going to multiply each of the reactants and product coefficients, which are 1/2, 1/2, and 1 respectively, by 4. So I end up with 2H2 plus 2Cl2 yields 4 HCl. And the other thing that I did was, if I multiply the coefficients in the balanced equation by 4, I also have to multiply the enthalpy of formation by 4. So I took 4 times negative 92.3 to get negative 369.2 kilojoules as the heat of formation for 4 moles of HCl. In this slide, we see the next step. We've got the coefficients all matched up, but now we need to make sure that what's on the reactant side in the reaction equation is also on the reactant side in our enthalpy of formation equations. So there are 2 equations that we need to flip here, and the 2 are: the first one, SiCl4, yields Si plus 2Cl2. We reverse that equation from the normal formation from its constituent elements. And when we do that, we also have to change the sign from negative to positive. Also with our water, we flip that equation so that water is on the reactant side in both the reaction equation and in the enthalpy of formation table equations. So that sign also goes from negative to positive. So that's the step we just took. So again, to reinforce, we're completing our table. We have flipped the reactions that needed to be flipped. We've changed the signs on the delta H of formations. We've made sure that coefficients match the coefficients that are in the reaction equation. And we're ready now to begin to add the reactions together. And then after we add the reactions together, we will add the enthalpy of formations together and get a final result here. Here are the results of adding the equation. The first thing we want to do is look at what reactants and products in our table of reactions are the same on both sides, and we can cancel them if they are the same on both sides. So we have 2Cl2 in the top equation and 2Cl2 on the reactant side in the bottom equation. Because they're on opposite sides, we can cancel those. When we look at our second equation down, we have 2H2 and an O2 on the product side, and we can cancel those with the 2H2 in the bottom equation and the O2 on the reactant side in the third equation down, and those will cancel out. Our silicon on the product side in the first equation will cancel out the silicon on the reactant side in the bottom equation. And at this point, we should be ready to add together what's left. And when we do that, we have SiCl4 in a liquid phase plus 2H2O in a liquid phase will yield SiO2 in a solid phase and hydrogen chloride gas. Everything is balanced, so we know that we canceled what we needed to cancel. We have the net reaction that we wanted, and now we just add the enthalpy of formations together, paying very close attention to the sign. And when we do that, we get a value of negative 69.6 kilojoules. And that is the correct answer. I hope your answer and your work matched mine. If not, you may want to go back to the beginning of the podcast and use a new piece of paper and see if you can work through this again and come up with the answer that matches the correct answer. Thanks. We've come to the end of the second part of the Hess's Law podcast series. This is part 1B, but it's really part 2 if I had numbered it correctly from the beginning. It is the end, and I'd like to leave you with a quote from a wonderful author. And Madeline says this: "Our truest response to the irrationality of the world is to paint or sing or write, for only in such response do we find truth." I wish you well.